So this is just a last example from the last lesson. It says determine the values of k such that x plus 1 is a factor of x cubed minus 7x plus k. So again, if it's a factor, that means it divides evenly into the polynomial, which means the remainder would be 0. So if you're going to use the remainder theorem here, p at negative 1 has to equal 0. Remember, you're always comparing the binomial to x minus a and asking yourself, what number would you have to put in for a so that x minus a becomes x plus 1? And a would have to be negative 1. The minus minus would become a plus positive. You get your x plus 1. So p at negative 1 has to equal 0. Thank you. So when I let x equal negative 1, the expression must equal 0. Negative 1 all cubed is negative 1. Negative 7 times negative 1 is positive 7. And negative 1 plus 7 would be 6. So therefore, k would equal negative 6. And you can check this. We're finding the value of k such that that x plus 1 is a factor. That means if you divide by x plus 1, you have to get a remainder of 0. We would change it to a negative 1 so we can add as we go, and that's going into 1x cubed. Once again, there's no x squared term here, so it doesn't change how remainder theorem is done. But when you're using division, synthetic or long, you have to put a 0 there for the 0x squared. Then you have the minus 7x, and then you have the minus 6 for the k value that we found. Right, we change it to an x minus 1 so we can add as we go. Negative 1 times 1 is negative 1, and we add. Negative 1 times negative 1 is positive 1, and we add. Negative 1 times negative 6 is positive 6, and we get the correct remainder when we add. So that just shows that a k value of negative 6 makes it so that x plus 1 is a factor. When you divide x plus 1 into it, you get a remainder of 0, which means it divides evenly. So again, that means that it is a factor. Okay? So let's start talking about 3.4 then, looking at the equations and graphs of polynomial functions. As in the case with quadratic functions, the zeros of any polynomial y equals f at x correspond to the x-intercepts of the graph and also the roots of the corresponding equation, f at x equals 0. For example, if you have f at x equal x minus 1, x minus 1, x plus 2, there are two identical roots at x equals 1 and a third 0 at x equals negative 2. These are the roots of that equation. If a polynomial has a factor x minus a that is repeated n times, then we say x equals a is a 0 of multiplicity n. So that function f at x equals x minus 1 all squared times x plus 2 has 1 0 at x equals 1, and its multiplicity is 2. It occurs twice because the factor is squared. So that means that it will occur twice. And then there's a third 0 of negative 2, and that one has a multiplicity of 1 because it only occurs once. Okay, Tyson, you with us? Okay, put your phone away, please. Thank you. So if we look at the graph then of x minus 1 all squared plus 2, and we talked about this yesterday, when a factor occurs twice, when it has a multiplicity of 2, the graph will bounce off the x-axis there. Okay? The values of y will not change from a negative to a positive or a positive to a negative. When we look at the x-intercept at negative 2, that has a multiplicity of 1, and the graph crosses the x-axis there. The values of y do change from negative to the left of negative 2 to positive to the right of negative 2. The graph goes from below the x-axis to above. But at the root of 1, and again that has a multiplicity of 2, the values of y do not change there. They're positive on either side of that root of positive 1. So that's what it means when it says the sign either changes or it doesn't. That means the values of y change from positive to negative or negative to positive, or they don't change, like in either side of positive 1. Okay, so that's what we're talking about. So it says graph each of the following cubic functions on the grids provided, discuss the multiplicity of the zeros. So we can sketch a graph of this. Because they're in factored form, we can get the x-intercepts just by looking at it. If x minus 3 is a factor, that would mean that positive 3 is an x-intercept. If x minus 1 is a factor, that means that positive 1 is an x-intercept. As well, x plus 2 is a factor, so negative 2 will be an x-intercept. And all of these, excuse me, x-intercepts have a multiplicity of 1 because it comes from a single factor. Each factor occurs only once. All right? But we also need to know a few other things to sketch this graph. One of them being the end behavior, right? This is in factored form, but if you multiplied out the 3 factors, you'd have a positive x times a positive x times a positive x, which is a positive x cubed. So if you have a third degree polynomial with a positive initial term coefficient, what does that mean, Judah? You need to stay with us, please, okay? Put your phone away. So that means you compare it to a line with a positive slope, because a line is an odd degree, and the third degree polynomial is an odd degree. And the initial term coefficient on a line means that it has a positive slope. It'll fall to the left, rise to the right. This will do the same. It'll fall to the left, it'll rise to the right. The initial term coefficient, the initial term, I should say, tells us that. The degree along with the coefficient. Finally, we can find the y-intercept. The y-intercept is where x equals 0. It is the constant term, which again is found by letting x equal 0. So if we take y equals, and we take the 3 factors and let x equal 0, 0 minus 3 is negative 3, 0 minus 1 is negative 1, 0 plus 2 is 2. When you multiply those 3 together, you will get positive 6. So we have a y-intercept up here, and we'll say that is at positive 6. Okay, now these graphs, these polynomial functions are always symmetrical between the x-intercepts, all right? So what that means, we've said that the graph will fall to the left and rise to the right, so it's going to have to come from below in the third quadrant and go up, and it's going to get to a point where there's a local maximum. It's going to come to a point where it reaches a maximum, and then it'll start going down again. The point where that occurs will be halfway between these first 2 x-intercepts. They are 1, 2, 3 units apart. So 1.5 units away, which would be at negative a half, the graph will reach the maximum point. So it'll be somewhere above the y-intercept of positive 6, and then it's got to go down, and it'll go through that next x-intercept. And then between the last 2 x-intercepts is where the graph will come to a local minimum point. Halfway in between would be at positive 2. So we know where the min and max values are for the x values, but we don't know what the y values are. And we don't need to know. Okay? You could, if you wanted to, let x equal negative a half in the equation and find the y value. That would give you this maximum point. You could let x equal 2 in the equation, find out the y value. That would tell you the y value of the minimum point. But we don't need it. We're just drawing a sketch. So there's a sketch of that graph. Okay? Now, for the next one. Here you've got a factor of x plus 1 that is squared. That means you're going to have an x-intercept of negative 1, and it will have a multiplicity of 2, which means the graph will bounce off the x-axis there, or the sign will not change. The values of y will either be positive on either side or negative on either side. We won't know until we figure out what the end behaviors are. We also have a factor of x minus 3, which means that positive 3 is an x-intercept, and that will occur only once, meaning the graph will cross through the x-axis there. not bounce off. Once again, this is a third degree polynomial. If you're multiplying out these three factors, this x would be squared times this x would give us x cubed. And it's a positive 1x cubed. So just like the last one, it'll act just like a line with a positive slope. Right? It's the third degree polynomial, so you compare it to a line. All right, Julia? You're with us? Okay. It'll fall to the left, rise to the right. So that's what this will do. It's going to fall to the left and rise to the right. And once again, an x-intercept of -1, we said, has a multiplicity of 2, which means the graph is going to bounce off the x-axis there. The other thing we'll get is the y-intercept. Again, our y-intercept is always where x equals 0. So you're going to get y equals 0 plus 1 all squared times 0 take away 3. 0 plus 1 is 1. 1 squared is 1 times -3 is -3. That's where our y-intercept is. Okay, so we have everything we need to draw a sketch. We know it's going to fall to the left. It comes up to this x-intercept of -1, and the graph has to bounce off of it. And then it's going to go down through the y-intercept, and then halfway between the two x-intercepts that we have, they are 1, 2, 3, 4 units apart. So 2 units apart, or at +1, is where the graph will hit the next minimum value and then go up from there. So we always put arrows on our graphs because that pattern continues on to infinity. So that's a sketch of that graph. The last one, we never saw one like this yet. Y equals x plus 2 all cubed. So this is the graph of y equals x cubed shifted 2 to the left. Right? This is a transformation of y equals x cubed. And because inside the bracket you have an x plus 2, the x is replaced with an x plus 2, that's an h value. Remember, whatever happens to the x happens to the x minus h. The x is cubed, so the x minus h is cubed as well. So this is the graph of y equals x cubed shifted 2 to the left. So what does the graph of x cubed look like? So what happens there, this is the graph of x cubed. It goes through the origin, but at the origin, at the point 0, 0, which is the x-intercept for y equals x cubed, it's also the y-intercept, there's what's known as a point of inflection there. The concavity of the graph changed. The first half of this graph is said to be concave down. The other half, on the right side of the y-axis, is said to be concave up. So the first half is concave down because it's like the left side of a parabola, a quadratic that opens down. The right side is like the right side of a quadratic that opens up. That's what makes it concave up. Okay? So the concavity changed at x equals 0. And it's known as a point of inflection, where the concavity changes. So the only thing we have to do now is just shift that graph to the left. We could find the y-intercept by letting x equal 0. You'll get 0 plus 2, which is 2. Cubed is positive 8. There's the y-intercept. Once again, the initial term would be positive 1x cubed, which means that it'll fall to the left and rise to the right. When the degree is odd, compare it to a line with a first degree. The initial term coefficient is still 1, so it will fall to the left and rise to the right. And again, at positive 2, we have what's known as a point of inflection. It's where the concavity changes. And that's what the graph looks like. So this is what happens when a factor is cubed. In this case here, we have a 0, a root, an x-intercept, a positive 2, and that has a multiplicity of 3 because there are 3 factors of x minus 2 here. And when you have a multiplicity of 3, you get a point of inflection there. So if we discuss the concavity for each of these, let's do it below. So each factor, I meant to say multiplicity, each factor here has a multiplicity of 1, which means that each zero has a multiplicity of 1. It occurs only once. And so what happens is that the graph crosses the x-axis. The values of y change from positive to negative or negative to positive. For the second graph, we have a factor of x plus 1 or a 0 of x equals negative 1, but this one has a multiplicity of 2. Whereas the other one, x equals 3, has a multiplicity of 1. Because the graph crosses through the x-axis there. And for the last graph, here we have an x-intercept at x equals negative 2, and this will be a multiplicity of 3. And when there's a multiplicity of 3, again, what happens is that the graph has a point of inflection there. When it's a multiplicity of 2, it's like the graph bounces off the x-axis there. And a multiplicity of 1, the graph goes straight through the x-axis. There's no point of inflection there. It just goes straight through. So this is some terminology that you need to know. There'll be likely a question somewhere on the diploma exam where you have to somehow address multiplicity of roots or zeros or x-intercepts or factors. So again, the multiplicity of a 0 is the number of times a 0 of a polynomial function occurs. The shape of the graph of the function close to the 0 depends on its multiplicity. When the multiplicity is 1, the graph crosses through the x-axis. When the multiplicity is 2, it bounces off. And when the multiplicity is 3, that's where we get that point of inflection, which again is defined there. It is a point on the curve at which the curvature or the concavity changes. So this is the graph of y equals x cubed again, and 0, 0 is a point of inflection. So for these examples, it says, determine the least possible degree, the sign of the leading coefficient, x-intercepts and factors, as well as where it's positive and where it's negative. And again, that refers to where is the graph above the x-axis. The y values are positive there. If the graph is below the x-axis, then the y values are negative. So that's what we're referring to. So to get the degree, there's two different things that you can look at. Number one, we've said that the degree tells you the maximum number of x-intercepts, but you can't always go by that because it is possible for a third-degree polynomial to have only one x-intercept. If you took this graph and shifted it up, let's say 22 units, then this minimum point, which is around negative 20, would be above the x-axis. And so in that case, it would only cross the graph in one spot. So you cannot always go by the number of x-intercepts, but we also said before, remember, the number of direction changes is always one less than the number of x-intercepts, or the degree, I should say. And so in this case here, you have two direction changes. You got that point there and that point there. Direction changes. This also means that if we go back up to this 0 with a multiplicity of 3, a point of inflection really means two direction changes. Because it's like the graph was going to change its, or keep this concavity, and then it changed its mind. Okay, so there's actually two direction changes there at a point of inflection. The other two graphs here have two direction changes as well. The number of direction changes is always one less than the degree. Okay, so again, because there's two direction changes for this graph below here, that means it would be a third degree polynomial. And so there's the answer to the first bullet. The degree would be 3. And in this case, you actually have 3 x-intercepts as well. So because it's a third degree polynomial, to get the leading coefficient, whether it's positive or negative, what is the end behavior? This graph falls to the left, rises to the right. A line that falls to the left and rises to the right would have what kind of slope, Vish? Take your earbuds out. Both of them. It would have a positive slope. So this graph must have a positive initial term coefficient. So we have a positive initial, and how does it ask us? I guess it asks for the sign of the leading coefficient. So a positive leading coefficient is what we'll write. And it's tempting to use, say, letters like LC for leading coefficient. It's tempting, but on a diploma exam, you won't get credit for that, okay? Because the marker doesn't know what the heck you're writing. They can assume, but markers don't assume anything. Okay, students have to show what they mean. So the x-intercepts and the factors of the function with least possible degree. Now, let's pause here and talk about what this least possible degree means, okay? For this first example, it can only be a third degree polynomial. That's the only option. However, whenever the graph bounces off the x-axis, all it really means is that that x-intercept has a multiplicity that is even. So just to show you that, if I go to y equals and I type in, let's say, y equals x minus 1 all squared. That'll be the graph of y equals x squared shifted 1 to the right. We would say that that polynomial, that quadratic, has an x-intercept of 1 with a multiplicity of 2. There'd be 2 of them. And the graph bounces off the x-axis. So we know what that graph's going to look like. But what if I take a different equation, let's say x plus 3, and in this case, raise it to the power 4 instead of 2? When I graph that, it also bounces off the x-axis at a different point, because instead of x minus 1, this one was x plus 3. So that gave us an x-intercept of negative 3 with a multiplicity of 4. But the graph still bounced off the x-axis there. Whenever the multiplicity is even, the graph is going to bounce off the x-axis. So when the graph bounces off the x-axis, it means the multiplicity is even. It could be 2, it could be 4, it could be 6, it could be 8. But that's why the terminology is used where it says the least possible degree. That's what that means. So it's only going to matter if the graph is either bouncing off the x-axis or also if there's a point of inflection. We've just seen that a point of inflection occurs when the degree is 3. But the same thing will happen if it's a degree 5 or 7 or 9 or any odd number 3 or greater. The same thing will happen. So if there's a point of inflection, though, we're always going to assume it's the least possible degree. You'd use degree 3 there. And if the graph bounces off the x-axis, we're going to use the least possible degree, so we will use degree 2 for that factor, that multiplicity. Okay, so back to this then, to finish this off, the x-intercepts and the factors of the function with least possible degree. So here we're going to have x-intercepts at x equals negative 4, negative 2, and positive 2. So therefore we will have factors of x plus 4, x plus 2, and x minus 2. And finally, we're asked to state where the function is positive and where it is negative. Again, that means where is it above the x-axis, where is it below. And it doesn't matter what we do first. If we start with the positive, this graph would be positive from -4 to -2. And I'm using interval notation here. And I have to use rounded brackets because at -4, the function is neither positive nor negative. It's 0. Judah, I'd like you to go sit out there, take your stuff and go. And then when I get a chance, I'm going to come and talk to you, okay? So at -4 and at -2, the function is neither positive nor negative. It's 0. So that's why we have to use the rounded brackets there. And also, from +2 to +infinity, the graph will be above the x-axis. Again, we have to use the rounded brackets there because at 2, the function is neither positive nor negative. It's 0. Okay? It's negative or below the x-axis from -infinity to -4, and as well from -2 to +2. That's where it's below the x-axis. So again, the rounded brackets must be used there because at the x-intercepts, the function is neither positive nor negative. It's 0. Okay? So the next one. First thing you can look at that graph, you should recognize that it's opening down, which means the degree has to be even. There are 3 direction changes here. 1, 2, 3, which means that it's a 4th degree polynomial. Remember, the number of direction changes is always 1 less than the degree, or the degree is always 1 more than the number of direction changes. So we knew the degree had to be even, but now we know that it will be degree 4 because there are 3 direction changes. Because it opens downwards, the only way a quadratic opens down is if the leading coefficient is negative. So the same thing has to happen here. The graph opens downwards, so this will have a negative leading coefficient. We look and we can see that we have x-intercepts at -5, -1, and +4. But that +4 has a multiplicity of 2. And then our factors would be x plus 5, x plus 1, and x minus 4, but the x minus 4 has to be squared. The graph bounces off the x-axis, so that factor, like the 0, has a multiplicity of 2. This graph is positive between -5 and -1, and that's the only place where that happens. Everywhere else, the graph is either on or below the x-axis. So we would say that it is negative, and we have to break up each interval. There's actually going to be 3 intervals here. The first being from -infinity to -5. The second being from -1 to 4. Again, because at 4, the function is neither positive nor negative. It's 0. And then after 4 to +infinity. You cannot combine those and say that it's negative between -1 and infinity, because at 4, the function is neither positive nor negative. It's 0. 0 is neither positive nor negative. So again, these look like n's or upside down u's. That's set notation. It means and. That's what it means. Okay? So there's that graph. So, example 2, we want to sketch the graphs of these polynomial functions. So it's in factored form, so that makes it nice and easy at least to get our x-intercepts. X minus 1 is a factor, so positive 1 will be one x-intercept. X plus 2 is a factor, so -2 is an x-intercept as well as -3, because we also have a factor of x plus 3. Each of these has a multiplicity of 1. So the graph is going to cross through the x-axis. The signs will change. Right? The values of y will change from positive to negative or negative to positive. This would be a third degree polynomial. If you multiplied out these three factors, you'd have a positive 1x cubed as your initial term, which means it's going to fall to the left and rise to the right. Compare it to a line with a positive slope. Right? We're comparing it to a line because a line has an odd degree. So a third degree polynomial acts just like a line. Just like a fourth degree acts just like a quadratic, a power 2. We can determine our y-intercept by letting x equal 0. So we'll have y equaling 0 minus 1, which is -1. 0 plus 2, which is positive 2. Thank you, and have a great weekend. So that's -6. There's our y-intercept. So we have x-intercepts at -3, -2, +1. This graph falls to the left, rises to the right. So we're going to come up through the first x-intercept. Halfway between the first two x-intercepts is where we'll have our local maximum, and then we'll come down. And the next two x-intercepts are 3 units apart. So halfway between them, or 1.5 units away, is where we'll get our next change in direction. And then the graph will go up through that next x-intercept. And there's a sketch. Okay? For the next one. This would be a fourth degree polynomial, right? That first factor of x plus 2 is cubed, meaning a multiplicity of 3. And then the other factor is just x. So when you multiply an x cubed by an x, you're going to get an x to the fourth. Also, the leading term here would have to be negative because you see you've got that negative in front. So this will act just like a quadratic with a negative initial term. It's going to open downwards. Fall to the left, fall to the right. We have x-intercepts of -2 and +4. But the x-intercept of -2 has a multiplicity of 3. So there's going to be a point of inflection there. Right? The x-intercept of -2, because it comes from a factor of x plus 2 that's cubed, means it has a multiplicity of 3 and therefore a point of inflection. We can find our y-intercept by letting x equal 0. 0 plus 2 is 2, cubed is 8. 0 minus 4 is -4. So that's going to be actually at +32. So it's going to be way up here. I'm labeling that as +32. So Our graph comes down from the third quadrant. There is a point of inflection there, which means that the graph like flattens out right at that point. Its concavity changes. And then it's going to go up through the y-intercept. The maximum point is going to be halfway in between these, our two x-intercepts, so somewhere up there, and then it's going to come back down again. So there's a sketch of that graph. And it's just a sketch, right? But the sketches need to have the correct x-intercepts, needs to have the correct y-intercept, as long as it's not something that is crazy large or small. And in this case, clearly show the point of inflection and the x-intercepts. Okay? So let's look at example 3. Talked about this before. We're going to write the equation with least possible degree for a cubic function with zeros of -2 and with multiplicity of 2 and also positive 3. And so because it just says and 3, that means multiplicity of 1 and also a y-intercept of 6. So we're going to see why knowing the y-intercept is important here. But we can start to build this equation, right? If you have a 0 of -2, that means x plus 2 would be a factor. But because it has a multiplicity of 2, that means that factor is squared. And you also have an x-intercept of positive 3, which means that x minus 3 is a factor, and it has a multiplicity of 1. Now, I mentioned before, there are infinitely many graphs or polynomial functions that we can come up with that have these characteristics, right? If I put this equation into my calculator, and in this case, we're assuming, and I'm going to put an a value there because we talked about that before. I mentioned it. If I just let a equal 1, what will it look like? So I have x plus 2, which is all squared, and I have x minus 3 as my factors. So if I graph that, that's what it looks like. But what if I change a to some other integer? So I'm going to draw a second equation. Let's say a is positive 2. So it's 2 bracket x plus 2 all squared times x minus 3. You all should know what it's going to do to the graph. It's going to vertically stretch it by a factor of 2. The y-intercept and every other y value will be multiplied by 2. The x-intercepts, though, will be invariant because the values of y there are 0. When you vertically stretch, you're multiplying the y values by the stretch factor. X-intercepts are where y is 0, so those points will be invariant. Different graph. Same x-intercepts, but different graph. What if I let a be, let's say, negative 1/2 or negative 0.5? So again, you should know from the work that we've done in the past that that's going to do 2 transformations to the original one. It's going to vertically stretch it by a half and also reflect it over the x-axis. So when I hit graph now, that's what happens. But all these graphs have the same x-intercepts with the same multiplicities. So that's why we have an a value in front. And we need to figure out what the a value is. And this is why you're given another point on the graph. It might be the y-intercept, or it might be some other point somewhere else. But if the graph goes through a y-intercept of 6, which again is the point 0, 6, it means that that point must satisfy the equation. When x equals 0, y must equal 6. This is how we figure out what the a value is. So 0 plus 2 is 2, squared is 4. 0 take away 3 is negative 3. So 6 will equal negative 12a. And when you divide both sides by negative 12, a equals negative a half. Right? So just by luck, I think that's the one that we graphed. Yeah, the last graph that we did was when y equaled negative 0.5. And if I go into trace and I make sure that I'm on that third equation, the y-intercept is 6. So it checks. It has the same or the correct x-intercepts with the correct multiplicity, and it also has the correct y-intercept. So again, it says determine the equation, so we need to write it with our a value of negative 1/2. There's our equation. And there was a question on January diploma exam in the written response where students had to determine the equation of a polynomial function. And so these are the things that you need to do. Just looking and getting the x-intercepts and writing the factors is not enough, because there are infinitely many polynomial functions that will have the characteristics of those zeros. What makes each one unique is another point. And it might be the y-intercept, or it might be another point somewhere else. But you need another point in order to figure out what the a value is. And again, the word determine means you need to show your work. You need to show what you did in order to get that a value. Example 4, Bill's preparing to make an ice sculpture as a block of ice that is 3 feet wide, 4 feet high, 5 feet long. Wants to reduce the size of the block of ice by removing the same amount from each of the 3 dimensions, and he wants the new volume to be 24 cubic feet. We're asked to write a polynomial function to model this situation. So again, the volume of a box is length times width times height. We know that the volume needs to be 24 cubic feet, and the length, width, and height are found by taking the original dimensions and removing the same amount from each of those dimensions. So if we let x equal the amount removed from each dimension, the length was 5, so we're going to remove x from that. The width was 3, we're going to remove the x from that. And the height was 4, we're going to remove the x from that. So there is a polynomial function. So to figure out how much it needs to remove from each of those 3 dimensions, we need to figure out what x is. We need to solve this now. Okay? So it will involve multiplying out those 3 factors and then making it equal to 0. So the first 2, if I FOIL that out, 5 times 3 is 15. The outer product is minus 5x. The inner minus 3x. That gives us minus 8x plus x squared. Times the 4 minus x. So now I'll multiply all 3 terms of the trinomial by 4 and then also by the negative x, and I'm going to simplify. So 15 times 4 is 60 minus 32x plus 4x squared minus 15x plus 8x squared minus x cubed. And now I'm going to simplify this and make it equal to 0. So if I subtract the 24 from both sides, that'll give me 36 here. Negative 32x, take away 15x is minus 47x. 4x squared plus 8x squared is 12x squared minus x cubed. Or negative x cubed plus 12x squared minus 47x plus 36 equals 0. And when you look at the question, how it's worded, how much should he remove from each dimension, it actually doesn't ask us to determine or algebraically find or anything like that. So on a diploma exam, you wouldn't have to show even this much. You actually would be able to stop right here and use your graphing calculator to solve this. Okay? Otherwise, if it was an algebraic approach, then you'd have to factor the third degree polynomial that we had to find out what x equals. But let's go straight to our calculator. We'll clear the equations that are there. And I'm going to put two equations in, the first being y equals 24, the second being those three factors, 5 take away x, 3 take away x, and 4 take away x. So that first equation, y equals 24, means that our y max has to be at least 24. So we can see that line. So when I go to my windows, let's set my y max to 30 and maybe change our scale to 5. Because we need to see the line y equals 24. So there it is. That's what that graph looks like. It has 3 x-intercepts, but it's where the two graphs intersect that we really care about. Second function trace, number 5 for intersect, enter, enter, enter. It intersects at x equals 1, so that is our answer. X must equal 1. And if we took this equation that we got here at the end and graphed it, there would only be one x-intercept for that because that's one equation equal to 0. It would be at x equals 1. Remember, some third degree polynomials will have only one x-intercept. The most it can have is 3, but it could only have 1. And this one would. There's only one answer to this, and that is x equals 1. So we can say, using the graphic display calculator, x equals 1, which means 1 foot needs to be removed from each dimension. Okay? So again, we're asked to sketch these graphs. So that first one would be a fourth degree polynomial. The first factor is cubed, which means that if you were to multiply out x minus 2 times x minus 2 times x minus 2, You'd get an x cubed out of that, but then you multiply by the last factor, which will give you an x to the fourth. This is a fourth degree polynomial with an initial coefficient that's positive 1, because they're each 1x's in the factors. So the initial term would be positive 1, x to the fourth, which means the graph will open up. It'll rise to the left, rise to the right. The fact that we have x minus 2 as a factor means that positive 2 is an x-intercept, as well as negative 1. But that positive 2 has a multiplicity of 3, which means there's a point of inflection there. The x-intercept of negative 1 has a multiplicity of 1, so the graph is going to cross through the x-axis there. We can find our y-intercept by letting x equal 0. And I think I mentioned this before on pretty much every diploma exam. Usually, well, sometimes it's multiple choice, sometimes it's numerical response, but there's usually a question where you have to find the x-intercept or y-intercept for a function. Y-intercepts always where x equals 0, x-intercepts always where y equals 0. So in this case, if we let x equal 0, we're going to get 0 take away 2. That needs to be cubed times 0 plus 1. 0 take away 2 is negative 2, cubed is negative 8, times 1 is negative 8. So our y-intercept is down here, and we'll say that that's negative 8. So again, the x-intercept of negative 1 only occurs once. It has a multiplicity of 1. So it's going to come down, it's going to go through the y-intercept, and then it's going to curl up towards the next x-intercept, but there's going to be a point of inflection there. So there's that graph. So it did say to state the characteristics, so we should do that. We have an x-intercept of 2 that has a multiplicity of 3. And then we have another x-intercept at negative 1. And that multiplicity is only 1. We've shown where the y-intercept is, but we can also say that this graph rises left and rises right. So there's the characteristics that we use to sketch this graph. Right? For question B, that's a third degree polynomial, but it has a negative initial term. So it's going to act just like a line with a negative slope. This one will rise to the left and fall to the right. Okay, so we can say this graph rises left and falls right. Now, in order to determine the x-intercepts for this, we're going to have to factor it. We've got negative x cubed plus 13x plus 12. Negative x cubed plus 13x plus 12. So we'll use our graphing calculator to find our first x-intercept. We'll put it in there, negative x cubed plus 13x plus 12. It looks like negative 1 is an x-intercept. Let's confirm that by going into our trace mode, and yes, it is. Negative 1 is an x-intercept, so x plus 1 is a factor. We would change it to x minus 1 so we can add as we go. and that's being divided into negative 1x cubed plus 0x squared. Right? There's no x squared, so we have to put a 0 there, plus 13x plus 12. That first term always comes down, and then we multiply and add. Negative 1 times negative 1 is positive 1, and we add. 1 times negative 1 is negative 1, and we add. Negative 1 times 12 is negative 12. The fact that we get a remainder of 0 tells us that we've done all our steps correctly. If x plus 1 is a factor, it has to divide evenly. You need to get a remainder of 0. So not only does this confirm x plus 1 as one factor, but the other factor is negative x squared plus 1x plus 12. And so we're going to factor that quadratic. Now, I would take out a common factor of negative 1 out of the quadratic, and it's a coefficient, so that's why I moved it in front of the first bracket. But that leaves us with positive x squared, negative x, negative 12. And the factors there are x minus 4, x plus 3. So that gives us our 3 x-intercepts, right? We're going to have x-intercepts of negative 1, positive 4, negative 3, and each of them will have a multiplicity of 1. Which means the graph is going to cross through the x-axis. The values will change. So 1, negative 4, negative 3. Positive 1, negative 3, negative 4. The constant term is positive 12. So that's where our y-intercept would be. Right? Remember, the y-intercept is always where x equals 0. When the polynomial is written in expanded form, not factored form, the constant term will be the answer you get when you let x equal 0. So our y-intercept is at positive 12. It is the constant term. So we can, put that right at the top and just say that that's positive 12. So again, this graph will rise to the left, fall to the right. It's going to come from up in quadrant 2. It's going to hit that first x-intercept, and halfway in between that and the next x-intercept is where it's going to change its direction. It's going to come up to another maximum and then come down to the y-intercept and then to that last x-intercept. And there's a sketch of the graph. We don't know exactly where the max and min points are, the local max and mins. There is no absolute max and min because this graph will rise to the left. It'll just keep going upwards to the left. So we don't know where those local max and mins are, but we don't need them. It's just a sketch. Okay? So again, let's go back to determining some equations. If you look at these graphs, you've got an x-intercept of negative 3 with a multiplicity of 1 and an x-intercept of positive 2, and that has a multiplicity of 2 because the graph bounces off the x-axis there. Finally, we have an x-intercept of positive 5. So again, that would be a multiplicity of 1. So we can start to write this equation in factored form, but we have to remember that we need to lead with an a parameter, or any letter you want. You need to determine what the initial term coefficient is, and that's what a represents. So negative 3 is an x-intercept, so x plus 3 would be a factor. That has a multiplicity of 1. Positive 2 is an x-intercept, which means x minus 2 is a factor. And again, we're always assuming the least possible degree. So that would have a multiplicity of 2 because the graph bounces off the x-axis. Technically, it could be a multiplicity of 4 or 6 or 8 or any even number. But we're going with the least possible degree. And finally, positive 5 is an x-intercept, which means x minus 5 would be a factor with a multiplicity of 1. And to determine A, we need another point. In this case, we're given, once again, the y-intercept is -2. So that will be when x is 0. Zero plus 3 is 3. 0 take away 2 is -2. All squared is 4. 0 minus 5 is -5. So -2 will equal 12 times -5 is -60a. And when you divide both sides by -60, a is going to have a positive value, which we knew it had to be positive because the graph is opening up. The value of a will actually be positive 1 over 30. And so our equation will be positive 1 over 30 times x plus 3, x minus 2 all squared, x minus 5. And you could put that in your calculator and you would see that graph. So you can check it. And to make sure, you'd have to have those same 3 x-intercepts with the same 3 multiplicities, and also the y-intercept would need to be -2. You could put it in your calculator and you would see that. When I look at question B, this graph again opens down. So it has to have an even degree, and a would need to be negative so that it opens down. We can figure out what the value of a is by starting with the factored form. -1 is an x-intercept, so x plus 1 would be a factor, and that would have a multiplicity of 2. You've got positive 2 as an x-intercept, so x minus 2 would have to be a factor, but that would have to have a multiplicity of 3 because there's a point of inflection there. And finally, you've got positive 4. Now I need to back up. That x plus 1 would need to be squared because that -1 x-intercept has a multiplicity of 2. The graph bounces off the x-axis there. And positive 4, so x minus 4 would have to be a factor, and that would have a multiplicity of 1. So this actually has a degree of 6. Because the first x is squared, the second x is cubed. That's a degree of 5 plus 1 more. And again, to find a, we need to use another point. The y-intercept is given. It's not always the y-intercept. Sometimes it'll be a different point. But the y-intercept is at 0, -4, which means y is -4 when x is 0. Zero plus 1 is 1, squared is 1. 0 take away 2 is -2, cubed is -8. And 0 take away 4 is -4. So -4 will equal a times positive 32. And when you divide both sides by positive 32, we get a negative value for a, which we knew we needed because it opens downwards. A will equal -1 over 8. And we can now write our equation for p at x. So the x minus 2 is cubed, the x plus 1 is squared. Because of what the graph does at those points. Thank you so much. Okay. So there is a worksheet, I think, there for you to, well, actually this one, and I'm going to stop now because I want to go through your chapter 2 quiz. So maybe on Monday we'll pick up these last couple ones. The only difference here is that the other point you're given is not the y-intercept, it's another point, but it's done the same way. Once you write your factors with the a in front, the point is 2, -6, so you'll let x equal 2, y equal -6 now to find out what a was. So we'll do one of these questions on Tuesday as we finish off this lesson. Okay, but I want to stop there for now so we can go through the chapter 2 quiz.